on human anatomy, physiology, pharmacology, behavior, communication, alongside skills and applications all into your brain. That's what I decided to do. And between sometimes shitty lectures, camps of teaching, and worldwide global events, a lot of this learning has not actually happened in the lecture theatre or in hospital, but it has had to be self-taught. So, as any other medical student, I have spent a significant proportion of my 20s just learning. And the single most life-changing skill I have taught myself is how to teach myself. So today, I thought I would completely break down and show you the step-by-step process that I use to teach myself especially very difficult topics to learn in a way that makes them digestible, memorable, and above all, applicable and interesting. This will be a combination of my own personal experience, tips that I've gained from reading the books of the most excellent teachers in the world, and also a bunch of evidence-based research around the human memory, brain, and learning. Let's get straight into it. There was this general consensus that neurology is a very difficult topic to study, so for the purpose of this video, I'm going to break down how I would study one topic in neurology, which is multiple sclerosis. So I have a 6-step process, of which the very first step is called broadening the context. And what I will be doing here is placing this topic in a broader context in the world and in my brain for it to make sense. Because at the moment, multiple sclerosis is just a chapter in a textbook or some questions in my exam. I don't particularly care about this. There's many chapters in many textbooks. There's no inherent curiosity in me to go, oh my god, I must know what this is about. And before you say, well, you spend a lot of money in university and if you don't study properly, then you're not going to pass your exams, this is not enough incentive for me to actually study things properly or care about the things that I study. So I need to place this in a broader context in order for it to make more sense and excite me a bit more. Words in a textbook, not exciting. Real life world, much more exciting. Richard Feynman, one of the best teachers in the world, identified this phenomenon when he said, I have to understand the world, you see. So he felt very, very strongly that people have an inherent curiosity about how things in the world work. And this is what I try to leverage. Before I study anything that is difficult, I need to put my curiosity about this topic and my emotional investment in this topic at the maximum level it can reach. And at the moment, it's just non-existent. Multiple sclerosis, couldn't care less. So let's make it very interesting for Elizabeth. Now, the way that I will do this is that I will go to Google and I will Google multiple sclerosis and I will go to the news tab. But what I'm looking here is for some sort of media case. This is not going to be the studies of new drugs being found because again, I'm just not interested in this enough at the moment. This will be, is there some celebrity who has it? Is there someone who died because of it? Is there some huge controversy around this? Because I know that my brain is much more likely to kind of attach to these interesting things than it's to attach to a list of molecules, which I don't kind of recognize at the moment. So still, there's no textbook here. I'm just on Google and I am searching for something related to multiple sclerosis. And what I found, this is going to work perfectly. So this is a Guardian piece on Selma Blair discussing her history with multiple sclerosis. Ideal, absolutely ideal. I don't know who this lady is, but she looks like she's famous. So this is a famous person that I can identify the disease with. And what I'm going to do at this stage is that I am going to kind of read this and place it in my mind. If I just read about multiple sclerosis in a book, there's nothing that can connect it to pre-existing things in my mind because there's no slot for multiple sclerosis in my mind at the moment. There's something around neurology, and yes, I can identify facts here and there, but if I'm just treating every single chapter as just random facts, they're all going to kind of disconnect at some point and not make any sense. So what I'm leveraging instead of my random science fact is I'm leveraging my curiosity and my understanding of the world in a much more layman sort of way, in a way that anyone would understand. And if this is written on The Guardian, I'm absolutely sure that everyone will understand. While I'm reading this, I'm going to be picking out things that stand out to me that I know that I can anchor to. Now, what anchoring is connecting things from my pre-existing strong memory to things that are specific to multiple sclerosis. And I want this connection to be as strong as possible. So therefore, this context is really, really strong. So let's have a look. She's describing her childhood. I'm going to be picturing her every time that I read these things. So it says that she's suffered from multiple symptoms that come and go. Okay, so this is very interesting. There's a bit here about her going to Florida on a holiday. And this is interesting because it's Florida specifically, which is really warm. I can remember that. And then she was a trip for Instagram, so paid influencer thing. She bought a tiny bikini and like Hermes shoes. Okay, very fancy. So they're on a yacht. Again, really strong imagery here going on in my mind. And what happened here was, unfortunately, when she was on the water, she couldn't move. Okay, so she jumped off the yacht and then she was kind of paralyzed. She thought she was paralyzed. She couldn't control her legs. She couldn't swim in the water. Okay, this is a very strong visual experience for me. Someone in kind of a tiny bikini and in Hermes shoes jumping off the boat. She probably didn't have the shoes on, but in my mind, jumping off the boat into the sea, cannot move. Okay, this is very strong imagery. Good. So then we move on. So what happens is that she had a Romberg's test. Okay. She ordered an MRI on the spot. She talks a lot about how no one had ordered her MRIs in the past. Okay. Oh, again, very, very good. There's a part where she speaks about using a cane at a celebrity event, which again is something quite rare that we don't get to see. She was crying quite a lot, unfortunately. Oh, bless her. Interesting. There are times when, okay, so there's times when both the dog pees in the house and she pees herself because she can't, so she probably has some urinary incontinence here. Okay, interesting. There's a lot of visual stuff here. Okay, so there was a lot of information here related to multiple sclerosis, which is probably quite similar to the list of symptoms I would be getting in a textbook. But in this case, they are being anchored to so many things in my brain. So I'm thinking yachts, I'm thinking Selma Blair, I'm thinking canes, I'm thinking dogs, I'm thinking peeing one's trousers, I'm thinking sometimes dancing, sometimes not being able to move. So there's all of these things. I'm building a very strong picture in my mind and I'm anchoring it specifically to this individual. So thank her so much for writing this article, and I think there's a book on this somewhere. So this has meant that I've put this neurological condition into context. Now I'm going to be focusing on step number 2, which has to do with emotional implications. And what this means is that if there is a very, very challenging topic, I need to make sure that I am fully emotionally primed to tackle this. And what this means is that I need to understand the consequences of not learning it and understand the benefits of learning it, and also try to convince myself or try to frame it in a way that I am genuinely itching to do this. This is the dopamine section of this study method. Dopamine is a neurotransmitter which is related to our anticipation of something. When we are anticipating something exciting, dopamine increases in our brain and we really, really want to do this thing. So this is what I'm trying to do with these sort of topics. So at the moment, yes, I'm slightly interested in her story, but again, there's many stories out there. Why would I specifically want to learn about multiple sclerosis? So because we know that the scarcest interest is desire, we want to go for the desire angle here. So I'm going to go back to the article and see what is something interesting here. What is something about future me that might be interested? Is there something that particularly might make me kind of compelled to learn more? So okay, I think the part that stands out to me the most was that she's been misdiagnosed her whole life, and especially there was the segment when she said, when she got diagnosed, she said she felt an adrenaline rush of emotion. It felt like giving birth, the release of it. And I've gone through this myself. When you get a diagnosis for something that you've had your whole life and you suddenly understand what that thing is, it can be so absolutely relieving and life-changing. And it's such a bittersweet but mostly sweet moment. I can really relate to her with this thing. And so I don't have multiple sclerosis, but I can see how she must have felt in some ways, in some capacity, with her experience. So now I'm emotionally invested. Now I know that this is one of those conditions that sometimes gets missed, that sometimes is misdiagnosed, that apparently some very few tests could have found. So for her, it was a positive Romberg's test and an MRI. So now I'm kind of frustrated and emotionally invested. Yes, I need to understand what the hell is happening here and why this is so important. I hope you can see at this point how I have a very, very vague clue about what this condition is, but I'm already much more likely to remember details about it, and also I'm much more likely to be emotionally invested in this topic. A huge neurology topic, which is just in the chapter in my book I could not have cared less about. Now I'm like, hell yes, this is absolutely awful. Let's learn about it. Let's study more. So now I get to part 3 of my study, which is the deep dive. And this is potentially the most controversial bit, because the way that I study difficult things is by narrowing down on one specific thing that I need to know about them, and then learning only about that and asking questions around it as and when they pop up. So let me try to explain this specifically. I don't do overviews because I find overviews tiring. Even if I'm excited about something, they make me bored about it. If I just read a whole chapter or a whole essay on MS, I couldn't care less. I will get bored halfway and I will stop doing this. But
at Honda, we know you have to drive through if you want to.
It's a long video, so I'll post a link if you're interested in it. But this gives you a different way of approaching studying, so it's something to look into. Richard Feynman, I also read his book. Well, what you end up doing is just try different things. It is a lot of trial and error. You try different things and then find what works effectively for you. And so we have our quiz tomorrow. Our quiz is going to be on not stoichiometry, on nomenclature. This is from the old exam, the one posted on the campus. It's going to be a combination of these old ones and the new ones. For the most part, all of them will be the same except for one. One that won't be an acid. But otherwise, you won't see anything new, I think. So you should work. There's no easy way for nomenclature. Maybe you can think of ways to connect it, like she does. But a lot of this is just tedious work sometimes. And tedious work you have to do because you want to learn the language of chemistry. Or you might not be tedious. A lot of these are important. I'm not sure how much time you want to spend on something like sodium bicarbonate. Sodium bicarbonate is baking soda. Baking powder is sodium carbonate. Fe2O3 is rust. Al2O3 is major ceramic. NO1, the molecule we hear in science. So different things you can do to remember these sorts of things. We'll have the quiz at the end of lab tomorrow. At the beginning of lab, we're going to spend the time working on experiment 8, this drawings with 3D structures, that kind of stuff. Were there any questions? Yeah, the titration lab, you should turn that in as well. If you have it, somebody already turned it in today. We're going to do one more calculation on it. I'll talk about it tomorrow. All right, so last time we left off at polarity. Did we finish this? Polar molecules and non-polar molecules? No. Let's take a look at this. The question comes up about polarity. Polarity just means there are two poles, usually dipole, a positive end and a negative end. You can have more than two poles, but we're not going to have something like that. And basically, we want to determine if the molecule is a polar molecule or non-polar molecule. With a polar molecule, you have to have polar bonds. And these polar bonds cannot cancel out. What I mean by that is like CO2 has polar bonds. Oxygen is more electronegative than carbon. And so what that's going to do is it's going to pull the electrons out of the oxygen. And so we show that with a bond dipole like this. The bond dipole shows the positive end and the negative end. So the positive end is carbon, the negative end is oxygen here. So we draw a delta. Delta plus means a partial positive, delta minus means a partial negative here. And the same thing here. But what happens is, and what we look for is canceling or cancellation of these bond dipoles. And the way to visualize this is if this were a tug of war. If the two oxygens were in a tug of war with carbon, one oxygen pulling to the right, the other oxygen pulling to the left, and then 180 degrees, what we say is these are equal and opposite. If these are equal and opposite, then they cancel one another out. And if they cancel one another out, then we end up with polar bonds, but this is a non-polar molecule. Non-polar molecule arise from two things. One, they have non-polar bonds. If all the bonds are non-polar, then the molecule will be non-polar. And so it doesn't matter what the shape of this is or what it looks like. As long as it has non-polar bonds, then it's a non-polar molecule. Or it could have polar bonds that cancel one another out. So CO2 is non-polar, but this is called formaldehyde. Formaldehyde would be polar. Because here we're going to have the carbon-oxygen. It's going to be a polar bond, but it's not going to be canceled out. In fact, hydrogen-carbon, these bonds are pretty much non-polar. And so those aren't going to really factor. And they're just very, very slightly polar, but essentially we just call them non-polar. And so there's nothing canceling this bond dipole out there. And so formaldehyde's polar. We want to know if something's polar or non-polar because formaldehyde, you should be able to dissolve this in water. That is, water is polar as well. And so polar molecules like polar molecules. So formaldehyde should like water, but does CO2 like water? CO2 doesn't like water. CO2 is non-polar. And so if you try to mix CO2 and water, for the most part, most of the CO2 will bubble out. If you mix formaldehyde with water, then it should mix pretty well. And this gives us, do you recall the solubility rules for molecules? I wrote it down a long time ago. Anybody remember?
Sort of.
Kinda, sort of.
Yeah,
Somewhere in the back.
it's like a
Something that could, yeah, iodine's non-polar. Iodine, even though it's non-polar, a little bit can mix, like CO2. Most of the CO2 will bubble out, but you can get a little bit of CO2 in water. I know, the solubility rules for ionic compounds were not, the solubility rules for ionic compounds were quite involved. Those are hard to memorize. A lot of people go, oh, those aren't worth memorizing. But, to bring it into a broader context, like she does, there are certain things that those can be related to, like, for example, milk of magnesia versus drain cleaner, or calcium EDTA versus sodium EDTA. Maybe those types of things, might help, but maybe not. And so, multiple sclerosis is a pretty big topic. Some of the things in chemistry you don't want to spend that much time. You don't really want to spend that much time thinking about one little thing. And so what you can do is you can have something maybe less deep that helps you remember. But the solubility rules for ionic compounds are a lot more involved than the solubility rules for molecular compounds. The solubility rules for molecular compounds are really simple. This is one sentence. Just 3 words. 3 words. Compared to so much, sulfates are all soluble except for this, all that other stuff. So this is what you do, like on a test. If you were asked, what are the solubility rules for molecular compounds, you think, and then eventually it will come out of your memory. Maybe it's not at the tip of your tongue, but maybe, hopefully it comes out before the time is up for the exam. That kind of stuff. But the other thing, maybe is speed of recall. The faster you can answer the simple questions, the more time you can have for the tougher questions. And so that's something I always thought about. Because at UCLA, everything's like pencils down, and then they click the time, pencils up, and then pencils down. If you don't put your pencils down at the end of the exam, then they come over and deduct points or something. I forgot. It's some horrendous deduction. Pencil isn't down when they call pencils down. You might just try to work that last second. Oh, I'm almost done. Just 3 more words I got to write down. But if pencils down was called, then you got to put your pencil down. Otherwise, you're going to deduct a huge amount of points. So that kind of thing. So that's another thing to train for, like recall information. And so things that you want to think about to improve, exam scores are always good. In our course, the exam plus the homework plus the labs plus the quizzes, we will be better for your percentage. But it's simple. This is the solubility rule for molecular compounds. Like dissolves like. You probably don't remember because you're thinking, like, what does that mean, like? Well, this is what it means. This is why we need to know about polarity. Because polar molecules like polar molecules, non-polar molecules don't like polar molecules, but non-polar molecules do like non-polar molecules. And so CO2 would much prefer to dissolve in oil, than in water, etc. And so it dissolves like. I didn't really talk much about it at the time I mentioned it because we haven't talked about polarity yet. Now, when we think about things adding up or canceling out in 3 dimensions, we have to look at the shape. It's very important that you draw the shape. So if we drew CO2 like this, which is fine, because does the Lewis structure have to be an accurate representation of the shape? And so if we drew CO2 like this, would they cancel out? No, it wouldn't cancel out. So we got to make sure we have the shape correct. Because in this case, if one oxygen is pulling up and this oxygen is pulling to the right, then net movement will be up and right. For BF3, as you recall, BF3 does not form an octet because fluorine will not double bond here. But for something like BF3, is this polar or non-polar? So the way I do this is, I think, well, you're going to have bond dipoles. And fluorine is more electronegative. This is why it doesn't double bond. Fluorine refuses to double bond because if it doubles bonds, it's going to donate electrons to boron. So think about a three-way tug of war. Well, what is the shape of this? The shape of that's trigonal planar, and the angles are all 120 degrees. So if there's a three-way tug of war, what would the net movement be from boron? None, because in this case they're equal and opposite. They all cancel out. Equal and opposite means non-polar. So BF3 is non-polar. If I change one of these, let's say I put, instead of a fluorine here, I put a hydrogen. If I put a hydrogen here, then they aren't going to cancel out. The boron-hydrogen bond is fairly non-polar, and it would become polar. How about this? CH2F2. CH2F2, is that nonpolar? Looks nonpolar because the two fluorines equal and opposite, and then the hydrogen. The hydrogen-carbon bonds are pretty much nonpolar, so we can ignore those. Is this nonpolar? The fluorine lone pairs? These lone pairs on what we call terminal atoms, we don't really pay much attention. If there were a lone pair on carbon, then we would worry about it. But when we have lone pairs on, that's why some terminal atoms you don't have to show the three-dimensional arrangement of the lone pairs. Mm-hmm. If the lone pair is on a central or a bridging atom, then yes, I want to see what it looks like. But ignoring the lone pairs, does that look non-polar to you or polar? Non-polar because the fluorines are equal and opposite. Would you say that?
Yeah.
No,
they're not equal and opposite, but it's all single bonds. Right?
They're all single bonds, yeah.
But because it's a tetrahedral, they're not quite.
They're not quite. Aren't they 180 apart?
Yeah, they do like
180. Are they 180 apart?
No.
No. In fact, they aren't 180. What are they? 109. And so if I were to draw this, let's put the fluorines in the plane of the page, 109. That means one hydrogen is going to wedge out and the other hydrogen is going to dash in. Yeah. Okay, now do they cancel out? No, they don't cancel out. Now one's going to be pulling up like this one's going to be pulling down like this. When we add those two up, we get what we call the net molecular dipole. The net molecular dipole is the point up and to the right. Do you see that? So we add these two up. If you had vector algebra, this is like vector algebra, so this arrow is a little bit too big. Smaller. And it turns out that this is what we call polar. And so it makes a difference how we draw the structure, because you might think it's non-polar because it's drawn like this, but a Lewis structure is not accurate. And so in order to get a more accurate representation, we got to draw three-dimensional. How about this? CF4. Is CF4 polar or non-polar?
Non-polar?
Yeah. CF4 turns out to be non-polar. I mean, if you add up these two, it points this way, but then if you add up these two, it points the opposite way. And the same thing, if you add up these two, it's pointing down this way, but it's going to be opposed by those two. You see, in other words, this is what we call spherical symmetry. It's like a ball. And so you're pushing on the insides of the ball equidistant, that is 109.5 degrees. Equidistant in 3 dimensions. And so this is non-polar. Everything cancels here, even though these are polar bonds.
So the polarity of like the molecule is based on like the charges then? Like when something
Yeah,
is...
right, on the charges. So basically, if we look at the bond dipoles, this is delta minus, fluorine's more electronegative, carbon's delta plus, this is delta minus, this is delta plus. And overall, when we have that, then overall the carbon is going to be delta plus. But if we were to average out the delta minus, you know, if I take this delta minus and this delta minus and average it, the average would be in the center here, pointed out that way. And so this would be the average of all the charges. And this would be what we call the dipole, molecular dipole. So the purple is the molecular dipole, the dipole is the monopole, and the blue are the bond dipoles. The dipoles are the individual bonds.
Is dipole like DI?
A dipole just means two poles, like a north pole and a south pole.
Like how do you spell it?
Oh, how do you spell dipole? So it just means D-I-P-O-L-E. Dipole. We have a dipole over here in the hydrogen fluorine. And fluorine is more electronegative, so it pulls the electron cloud closer to it. So we see it as like an asymmetric rather than a symmetrical electron cloud here. And so there's more, in other words, fluorine has a stronger pull for the electrons, so the electrons spend more time around fluorine. If electrons spend more time around fluorine and less time around hydrogen, then the fluorine is going to acquire negative charge and the hydrogen is going to acquire positive charge. But it's not a full charge because the electrons have not completely left hydrogen. And so these are partial charges. This is what happens in HCl. The chlorine is negative, the hydrogen is positive. And so we have electric field here. If the electric field's off, then the orientation can be in any three-dimensional spatial orientation. The molecules can be. But when you turn on the field, then there's a preferred orientation. And that is, the field is, it charges negative, so the positive end will be attracted to that. And this one's positive, the negative end will be attracted to that. That's the electric field line. Electric field is just some power supply or battery there. It's forcing electrons onto the blue and pulling electrons away from the red. Unfortunately, I don't know why science do that. It makes sense that the positive is red. If you think about batteries, the positive terminal is always red. Negative is usually black. In this case, they're calling the positive red. However, we have something called the electrostatic diagram. Yeah. If we look at the electrostatic diagram for HCl, take a look at that. Take a look at this. Remember this. Hydrogen is red, chlorine is blue. The positive is red, negative is blue. What did I say was red? The positive or the negative? Positive is red, negative is blue. But apparently, the people who decided to color code the molecular dipoles decided to do the opposite. And so, if you look at chlorine here, chlorine is red, hydrogen is blue. So just keep that in mind. Here in Chem 1A, it's just flipped. It's opposite of what you expect. Why? I don't know why. It was just, just arbitrary. But they decided to do it this way for that, and for batteries, they did it the other way. So whoever was doing the theoretical work for this didn't know batteries. Well, anyway, that's later on when we get to that chapter 20. So here's the CO2, the bond dipoles here. Here's H2O of the bond dipoles. And H2O of the bond dipoles do not cancel out in 3 dimensions. The molecular dipole is equal to the sum of the bond dipoles in 3 dimensions. So when we sum up the bond dipoles here, they cancel. When we sum up the bond dipoles here, they don't cancel. Water is such an important molecule, and water is polar. And so we want to know how water interacts with other molecules. So like HCl and water mix. They like each other. Ammonia and water mix. They like each other. Both are polar. But CO2 and water don't mix. Oil and water doesn't mix. Oil, you can have very complicated structures for oil. And so oil are what are called hydrocarbons. And so even if you have the most complicated structure, let's see. Actually, this isn't being asymmetrical. Let's try. Something like that. If you ever look at this 3-dimensionally, it's going to be kind of asymmetric. It's not very symmetric. But it doesn't matter the structure. All the bonds are nonpolar. The shape does not matter. All bonds are nonpolar. I mean, they're just slightly, very, very slightly polar. And therefore, you add up all the zeros over 3 dimensions, you can have a 0. Here's some more examples. CH4 is a hydrocarbon, so we don't even care. The bond is nonpolar. If the bond's nonpolar, then the whole molecule is nonpolar. CCl4 is also nonpolar. We have 4 chlorines, but it's in tetrahedral spherical arrangement. And So all the bond dipoles cancel. These have polar bonds. You can see here, but they all cancel when I'm there. CHCl3 is polar. Okay? These don't cancel. And so there's going to be a molecular dipole. They're showing the net molecular dipole, which is kind of pointed out like this. In between, this is like the tripod base. And so the dipole would stick straight out from here. This looks like a weird angle. CH2Cl2, this is polar. This is what we talked about earlier. CH3Cl, this is going to be polar. This one. And non-polar there. All right, so we want to determine, if we have a polar molecule or non-polar. It looks like it for this chapter. All right, so that was chapter 13. Any questions from chapter 13? What we're going to do is we're going to move on to chapter 14. Chapter 14 deals with gases, but we already had a chapter on gases. This is called Gases Revisited. So from the earlier stuff on gases, do you recall what the density of gases are roughly? What's the approximate density of a gas? It doesn't have to be exact, just something close. If I said, let's say, 40 grams per milliliter, would that be a reasonable density for a gas? Or
Was it like less than 1 or something?
less than 1? Okay, how about 0.5 grams per milliliter? Would that be a reasonable density for a gas? 0.5 grams per milliliter? Sure. Or just how about low? Gases have low density.
Yeah.
Yeah, but the problem is whenever you say something like that, somebody always asks, well, how low? Like 0.5? Like 0.1? You start getting questions like that. And so, speaking of studying, a lot of people don't really care for reference points, but we need reference points. The first time I moved to, I moved to South Bay area here, Torrance, and I thought, okay, I'm going to drive to the beach. So I started driving. I think I was on like Sepulveda or something, and I kept driving, and I wasn't getting closer to the beach, so I was worried. And it turned out I was driving the wrong way. I was going inland versus towards the beach. I had no idea because I didn't have any reference points. So I looked for reference points like tall buildings or something, but there are no big tall buildings in the bearing or in the mountains. I didn't see the mountains at the time in the car. I had no idea. I had no idea which way was up or down. The same thing happens in science, so you need some reference points there. And so 0.5 would be about the density of wood. Density of wood is about half as dense as water. Gases have a density like 1 gram per liter, about 1,000 times less. So, what I do is gases are about 1,000 times less dense than air. not air. Air is a gas. 1,000 times less dense than water. Water is a liquid. And so it's useful to know. Do you know the density of water? Yeah. 1 gram per milliliter, roughly. Now, density of water changes a little bit with temperature, but those are reference points. Those are also useful. And sometimes on tests, people will ask you questions like that, just straight memorization. And you go, there's been a big push away from memorizing things, but there's a certain minimum amount of stuff you have to memorize. Let's say I wanted to learn a new language. If I want to learn a new language, well, I don't want to memorize anything, right? Because you can always look it up. Are you going to be able to? Well, I guess you could speak. You just look it up each time. But you can do the same thing, except on tests you can't look it up, unfortunately. With some basic knowledge. Yeah. Well, air has a density around 1 gram per liter. And so this is another reference. Air has a density around 1 gram per liter. Water has a density of around 1 gram per milliliter. And so air is about 1,000 times less dense. But, everybody says helium is lighter than air. Well, how much lighter than air is helium? 1,000 times lighter? I don't know. And so we want to know certain things. Not only do we want reference points, but we want to know what's a reasonable range of things that you might expect too. And so it's not a huge amount of memorization. I'd like to know like the high and the low. It's actually not so hard to figure out how much less dense helium is, but helium is less dense than air, and so helium will rise up. Hot air is less dense than cold air. So here's this balloon. Well, anyway, we're going to revisit gases, and the first thing we're going to take a look at are mixtures. But let's review some stuff here. These are things from chapter 4. Gases can be compressed. Gases consist mostly of empty space. Gases can be expanded, so they can be compressed and expanded. If they're expanded, you just get more empty space. It may take work to do that, but it can be done. Versus liquids and solids. Liquids and solids aren't really compressible or expandable. All gases have low densities compared with those of liquids and solids. And so we know low density, but as you go on in science, you're going to have to know, what does that mean? How low a density? 1,000,000 times less dense? 1,000 times less dense? 100 times less dense? Half as dense? And so this is not, if I'm going to memorize something, I guess low density, yes. But it would be better if I had the number. 4, gases may be mixed in a fixed volume. It's easy to mix gases because there's lots of empty space. So there's plenty of room to make mixtures. And so we'll spend a little bit of time talking about mixtures in this chapter. A gas exerts constant uniform pressure in all directions, including the ceiling. And so these are things we talked about earlier, chapter 4. Here's a gas mixture. This is air. Air consists mostly of nitrogen and oxygen. There are other components to air too, like argon, noble gas, water vapor. If it's humid, it could be dry air. If it's dry air, then there's no water vapor. Maybe CO2 and other gases, including helium in there. And so here what they're doing is they're compressing the air into the tire that is going from a larger volume to a smaller volume. And so the pressure is going to go up. So we talked about this earlier. There's something called kinetic molecular theory. This is the way we visualize it. what's happening in the gas. And so let's take a look. This is from chapter 4 as well. A gas consists of molecules in empty space, mostly empty space. The volume occupied by the molecules in a gas is negligible when compared to the volume of the space the molecules occupy. And so, this is something we call an ideal gas. An ideal gas, you look at the particles, and the particles are tiny compared to the volume of gas. So let's say I have 1 liter of gas here, and it's practically all empty space. And so it's going to be about 1 liter of empty space. The particles barely take up any volume. All right, this will be not so ideal. Not so ideal is if I compress it. So what I do here is I'll take this and just compress it in a very small volume. And here, the volume taken up by the particles themselves is significant. And so volume of particles, significant. Here, I just make sure that the box is so big that the volume of the particles is not. The volume of the particles is not significant. And so what that does is when I go to not so ideal, it screws things up in the sense of pressure. Example, here, when the gas is ideal like this, if I cut the volume in half, you know what happens to pressure? So if I compress the volume to half, the pressure is going to double because of the same number of particles in half as much space. But when a gas isn't so ideal, if I cut the volume in half, then you would expect the pressure to double, but other things can happen. You can have nonlinear behavior. And so this is the kinetic molecular theory of an ideal gas. In an ideal gas, the gas is mostly empty space. In an ideal gas, the volume occupied by the molecules is negligible. In an ideal gas, the attractive forces among molecules of the gas are negligible. You know, what tends to happen is the molecules get closer and closer to one another, they can interact more with each other. So for example, over here, the molecules are so far apart from each other. There's a molecule here and then there's a molecule here. They're so far apart, they don't interact. However, if you keep compressing this and compressing it, eventually these molecules or particles, they don't have to be molecules. The particles of the gas can interact. So for example, helium, you know, if you keep compressing it, helium can end up liquefying, turn into a liquid. You know, the helium atoms attract one another. So we could do this by cooling it down. Or, you know, it depends. We could liquefy lots of gases. We can get liquid argon, liquid nitrogen, liquid oxygen, you know, if the particles can interact. And so to keep the gas behaving ideally, we want to make sure the attractive forces among the molecules of gas are negligible. One way to make sure the attractive forces are negligible is to have mostly empty space. But when you don't have that much empty space, then the attractive forces could be more significant. The attractive forces vary, though. Helium has very weak attractive forces. Whereas, like water, steam has pretty strong attractive forces. So steam, it's easy to liquefy steam into water. It's hard to liquefy nitrogen in the air or oxygen in the air. It's hard to liquefy helium because the interactions are so much weaker. Okay, the average kinetic energy of gas molecules is proportional to the temperature. Let's say average. So if this gas were at room temperature, 25 degrees C, all the molecules aren't moving the same speed. Some are moving faster, some are moving slower. And then we're going to just have some kind of average speed that they move. The average speed that they move is what we call the average kinetic energy, and that average kinetic energy is directly proportional to temperature. If we cool this down, then we're slowing the molecules down. We're slowing the average kinetic energy. If we slow the average kinetic energy, then they can interact. And so to keep ideal gases ideal, what we want is we want this. We want low pressure and high temperature. Low pressure and high temperature is more ideal. And what that pressure and temperature is varies on what the gas is. So for example, helium, low pressure would be considered 1 atmosphere. And high temperature would be considered anything above 4 Kelvin. But for steam, that changes. High temperature has to be above 100 degrees C, otherwise it's going to liquefy. When we have not so ideal gases, we get not so ideal gases at high pressure. At high pressure, the particles of the gas are crowded. And low temperature. Not so ideal gases often are called real gases versus the idealized gas, the ideal gas. Turns out there's no such thing as a perfectly ideal gas. The most ideal gas that we have is helium gas. And even helium gas will condense into a liquid at 4 Kelvin. But under normal conditions, helium's pretty ideal. And nitrogen and oxygen are pretty ideal under normal conditions. Steam, however, is not so ideal. The steam wants to liquefy or condense. All right, so when we take measurements on a gas, there are 4 things that we want to know about the gas. We want to know the pressure, the volume, the temperature, and the amount, N. It turns out the ratio, pressure volume over N and temperature, this ratio is equal to constant. And so as long as it's equal to constant, then it doesn't change. So we could change certain parameters of the gas, that is the pressure or the volume, or multiple parameters. We can add some gas or remove some gas, and then we get the combined gas law. Combined gas law. This is the Chem 1A version of the combined gas law. This is the Chem 4 version. The Chem 4 version of the combined gas law doesn't have N. It doesn't have N because there are no problems in our Chem 4 book that have gas leak out of the container or where you force more gas into the container. That is, in Chem 4, the amount of gas is fixed. In Chem 1A, you might increase the amount of gas in the container or decrease the amount of gas in the container, and that's going to change the other parameters. So this is from chapter 4. That constant has a special name. It's not just any old constant. This is called the gas constant. And the gas constant is given a symbol, R. So PV over NT is equal to the constant R. Rearranging this all in one line, we can get PV equals nRT. PV equals nRT, this is the ideal gas law. The ideal gas law works great if the gas is behaving ideally. But if the gas starts to deviate from ideal behavior, that is ideal conditions, the ideal gas law is going to be an error. And what we have to use are the real gas laws. The real gas laws are beyond the scope of Chem 4. The real gas laws are dealt with in Chem 1A. In Chem 1A, you can have more extreme conditions in which the gas doesn't behave so ideally. In Chem 4, we're just going to have normal conditions and normal gases, for the most part, behave ideally. What we have to do is we have to modify the ideal gas law to account for these things that real gases might encounter. Oops, I jumped ahead. All right, I didn't talk about this N much in here. Let's talk about N a little bit more. The ideal gas law is a composite of three simple gas laws combined into one. It's Charles' law, Boyle's law, and Avogadro's wrapped up into one. Charles' law and Boyle's law were in chapter 4. Avogadro's in chapter 14. You don't need to know the names for this. Avogadro's law is pretty simple. The amount of moles, the amount of gas is directly proportional to the volume. So if we had twice the volume of helium, then we have twice as much helium. 3 times the volume, 3 times as much helium. As long as the pressure and the temperature don't change. So that's what they say here. At the same temperature and pressure, so this is Avogadro's law here. So Avogadro says that it doesn't matter what the gas is. I could have 4 particles of oxygen. It's going to take up this much volume. If I replace this instead with 4 particles of hydrogen, it takes up the same amount of volume. So 4 particles of hydrogen would take up the same volume. However, if I had 8 particles of hydrogen, they'd take up twice the volume. Just like if I had 8 particles of oxygen, it would take up twice the volume. And so the volume is directly proportional to how many moles or how many particles I have. Over here, this is 8 particles of H2O gas, and it's going to take up this much volume here. And so Avogadro's law is if I double the volume and the pressure and temperature are the same, then I'm going to double the amount. I'm going to double the volume, double the amount. So we have the law of combining volumes, which essentially is Avogadro. So if I look at this reaction, this is the reaction between hydrogen and oxygen. Actually, we'll write this down for O2 gas plus hydrogen gas. And we'll need two hydrogens. This is going to form two H2O gas. This is the mole ratio. Is also the volume ratio. As long as all gases are at same temperature and pressure. So let's say all the gases are room temperature in 1 atmosphere, then this works. However, if you said the oxygen is at this temperature and pressure and the hydrogen is at a different temperature and pressure, then it doesn't work. Because the temperatures and pressures are different. And so the mole ratio here, 1 mole of O2 plus 2 moles of H2 yields 2 moles of H2O gas. This is normally H2O is a liquid, but in this case, we want it to be a gas. Do this. So the volume ratio would be this. It'd be whatever volume you want. So this could be 1 gallon of O2, 2 gallons of H2, yields 2 gallons of water, but we use liters mainly. So 1 liter of O2 plus 2 liters of H2 will give us 2 liters of H2O gas. So from the mole ratios here, we get mole ratio conversion factors. From the volume ratio, we're going to get volume ratio conversion factors. So let's look at this reaction here. This is Avogadro. If I look at the reaction between hydrogen and chlorine, they react in a 1-to-1 mole ratio. And this is going to produce 2 HCl gas. This is an element plus element redox reaction. So if I use 1 mole of hydrogen, how many moles of chlorine will I produce? If I use 1 mole of hydrogen, how many moles of chlorine do I need? 1 mole. And how many moles of HCl do I produce?
1.
Well, in this case, it's 2.
I thought you meant like 1.
Okay. Oh.
Yeah.
Well, sorry. 2 moles. Like that. Okay. So that's a mole ratio. We know that. And so if I had, let's say I had 4 moles of hydrogen, how many moles of chlorine would I need? I need 4 moles of chlorine. And then I'm going to produce how many moles of HCl? 8 moles. Well, Avogadro's law says this. If I have 1 liter of hydrogen, how many liters of chlorine do I need? I just need 1 liter. And how many liters of HCl gas would I produce? 2 liters. And so here's Avogadro's law in action. If I have 1 liter of hydrogen, I'm going to need 1 liter of chlorine, and I'm going to produce 2 liters of hydrogen chloride gas. And it's basically just the particles here. Here you can see it visually, and it doesn't matter what the particle is. It's 1 particle occupies this much space. It's mostly empty space. So I know chlorine's a little bigger than hydrogen, but since it's mostly empty space, they occupy the same volume. They aren't going to weigh the same amount, though. Chlorine's going to be heavier. And then when I react these two together, I form 2 moles. Yeah, so 1 liter plus 1 liter yields 2 liters. That's what should happen. This is wrong. What's wrong with this? This is wrong. You see what's wrong with number 3? See? What does not happen? Why doesn't this happen? There's something wrong with that picture. Maybe they aren't at the same pressure. Because now if I cram in 2,
Not the right picture.
the pressure will be double here, right? Twice as many particles in the same box, and we're going to double the pressure. So this is wrong. This is wrong. So the third one is wrong. How can I fix the third one? Make it. And so let's fix that one. We're going to just do it in liters. It shouldn't have been, if I took 1 liter of chlorine, which looks right, so the chlorine is going to be 1 liter. And chlorine is usually written in green. Hydrogen is usually in white. Just make it black. But I have 2 hydrogens here. If I have 2 moles of hydrogens, Avogadro's law says it's going to occupy twice the space as 1 mole of hydrogen. And so, in other words, well, this is not mole. I have twice as much hydrogen here in chlorine. And so, how many liters of hydrogen? I'm going to have 2 liters of hydrogen. Takes up twice the space. When I react these, I'm going to get 2 HCl's as before, but one of the H2s is not going to react, so I'm going to have excess hydrogen remaining. So how many liters should I have at the end of this? I should have 2 liters from the HCl, and I'm going to have 1 liter from the extra hydrogen. So this is my 2 liters of HCl, and I'm going to have 1 liter of unreacted hydrogen. There's only one of these reacted. The other liter did not. Does that make sense? So altogether, how many liters am I going to have at the end of this? 3 liters. And so visually, this is wrong. If I'm doing this using Avogadro's law, then I should have 2 liters plus 1 liter is going to give us 3 liters. Like this. Then it would be correct. Here we can see. Okay. When we have 3 particles, we double it to 6, it's going to take twice the volume. And then triple it to 9, it's going to take 3 times the volume here. Avogadro. All right, so let's take a look at, these are some reactions here. Let's just look at gas mixture using Avogadro's. And one other way of doing it. There are different ways that we can represent gas mixtures. And let me tell you about those. Gas mixtures we can visualize as mole fractions or mole percentages. volume fractions and volume percentages and pressure fractions. The volume fraction, volume percent, this is Avogadro's law. The pressure fraction and the pressure percent is another law, which I haven't talked about yet, and that's called Dalton's law. Mole fraction is always true. So let's look at air. I'm going to have 1 liter of air and 1 atmosphere. Air consists of 21% oxygen. Is the 21% oxygen, is that by mass or by number or moles? So if it's by number of moles, then if I had 100 air molecules, then 21 of those would be oxygen, and 79 of those would be nitrogen. Let's just assume that. Oxygen's usually red, nitrogen's usually blue. They're diatomic, but I'm just going to draw them like this. So air is 21% oxygen, O2, and 79% nitrogen. There's other stuff in there. We're going to ignore the water. We're going to ignore the CO2 and everything else. So what do you think? By mass or by mole or number? That's more beginning class. Did you do the calculations yet? Yeah, I wanted a percent error. You'd do it on a separate sheet.
So did you want us to just write the percent error like?
You can do that way. That's fine. Okay, we'll get started again here. Well, I recorded it earlier today, the gas mixtures. I just erased it. We'll do another example of the mixtures at the end. The common applications for the ideal gas law is you just solve for one unknown. So we'll take a look. Ideal gas law is a combination of these three laws we talked about earlier.
Is that percentages? So a mole sample between a fraction.
So a 0.592 mole sample of helium was found to occupy 14.7 liters when measured at 12 degrees C and 0.942 atmospheres. From these experimental data, calculate the value of R. So actually, we're only missing R. We're given PV and NT. So R is equal to, what is it? R is equal to PV over NT. And so we plug in the pressure. The pressure we usually leave in liters. So what was the pressure they gave us there? 14.7 liters. V is usually, that's V. P is in atmosphere, 0.942. I have these backwards, but it doesn't matter. Atmosphere divided by N, which is going to be in moles, 0.592 moles, and T, which we need in Kelvin. So this is going to be 273 plus 12. It would be 285 Kelvin. And so let's go ahead and calculate this here. So 14.7 times 0.942 divided by 0.592 divided by 285. We have 0.08207. Units would be liters times atmosphere divided by mole Kelvin. And so we can determine what R is. What you do is you do a whole bunch of measurements and then average it. And so average many measurements to get the average R value. So the accepted R value is 0.08206 liters times atmosphere per mole Kelvin. And this is to 4 sig figs, so it's not an exact number. So this is the accepted value. So you just run a whole bunch of experiments and measure it a bunch of times and then average that. And this is what we'll use for our R. So this comes out close. You end up using R so much that it's easy to remember. That is, if you don't have too many R values. Our book likes to do this. Our book likes to have you learn a bunch of different R values with different units. So the R value that we use is this, in liters atmosphere per mole Kelvin. What if we use, instead of atmospheres, what if we use torr? If we use torr, then we're going to get a different number here. Or what if we use milliliters? If we use milliliters, we're going to get a different number here. So the easiest thing to do is just to make sure that you convert everything as necessary, as required. And so there's no degree C here. We need to convert it to Kelvin. So we did the conversion here. What they'd like you to do is they'd like you to memorize this one. This is another R value. This is the R value if you're dealing with torr. And so this would be 62.4 torr times liter per mole Kelvin. But if we have too many different R values, because we need another R value if we're dealing with bar instead of atmospheres or torr. And so we're going to have too many different R values. And so the easiest way to remember this R value is just to use only one R value. We're going to use one R value and then convert everything as required, rather than have multiple R values. And so in this particular problem here, they want us to calculate R at 23 degrees C, 656 milliliters, 0.0298 moles, and 839 torr. So rather than calculating R values for all kinds of units, we'll just change those units to get the same R value. And let's see how close this one comes out. And so R is equal to PV over NT. Now the pressure is 839 torr. So 839 torr, we'll just convert that into atmospheres. 1 atmosphere is equivalent to 760 torr. Exactly. And then the volume's in milliliters, we're going to convert that to liters. So 656 milliliters is 0.656 liters. Divided by N, which is in moles, 0.0298 moles, divided by T. T is 23 plus 273, which would be 296 Kelvin. And so my preference is not to memorize a whole bunch of different R's, or just to memorize one R and then convert everything else. 839 divided by 760 will give us atmospheres times 0.656 liters divided by 0.0298 moles divided by 296. This one is a little bit higher, 0.08210 liters atmosphere per mole Kelvin. So we're going to see some variation. What we need to do is we need to average a huge number of these. Here. Or we can also get this theoretically as well, but from an experiment, we take a large number of measurements and then average it. Okay, so that's an example of solving for R. Typically, we don't solve for R. We just use this R value and then solve for other things. Okay, that's determination of a single variable. So what volume will be occupied by 0.393 moles of nitrogen at 0.971 atmospheres and 24 degrees C? So volume is equal to nRT over P. So we have how many moles? 0.393 moles. R is 0.08206 liters times atmosphere per mole Kelvin. That's the R value there. Times T is 24 degrees. So 273 plus 24 is 297. Kelvin. Divided by P. The pressure here is 0.971 atmospheres. And so we just take a look at the units. The moles cancel, the Kelvin cancel, the atmospheres cancel, and that leaves us with liters. Liters is what we want. And so we can go ahead and calculate this. 0.393 times 0.8206 times 297 divided by 0.971. 9.864. 9.864 liters of nitrogen gas. So let's see what they got. Yeah. They got 9.87 liters. They got 9.87 liters because the R value they're using is to 3 sig figs. And so if you look at the R value that they use 0.0821. For Chem 4, you need 3 sig figs is enough. You don't need 4, but for Chem 1A, you need 4 sig figs. And so if you're continuing on in Chem 1A, it's just best to use this one instead of the 0.0821. Okay, take a look at some other ones here. All right, there are other applications for this. One of the applications is molar mass, mm, we call it here. So the first application is just solving for a single variable, whether it's R or volume or any of the others. Number 2 will be molar mass of a gas. Molar mass of a gas, which will abbreviate mm. The molar mass of anything is equal to the mass in grams over moles. Mass over N. And so grams per mole. What we're going to do though is for moles, it's hard to measure that, but we can relate moles using the ideal gas law. The moles is equal to PV over RT. And then what we're going to do is we're going to substitute this in up here. So we're going to get the mass in grams divided by PV over RT. We're going to invert and multiply. So we're going to get the mass times RT divided by PV. And so this is an equation for molar mass of a gas. We'll have to measure the mass, the temperature, the pressure, and the volume. And then we can determine the molar mass. So let's look at their example here. A researcher vaporizes 1.67 grams of the liquid at a temperature of 125 degrees C. So they converted the liquid into gas. So mass is conserved around 1.67 grams of gas at 125 degrees C. Its volume is 0.421 liters at 749 torr. Calculate its molar mass. And so in this example, the molar mass is equal to the mass, 1.67 grams, times R, 0.08206 liters atmosphere per mole Kelvin, times T. Temperature is 125 degrees C. That's going to be 273, I'll just write it here, 273 plus 125. Kelvin divided by P in atmospheres, but they didn't give us P in atmospheres. They gave us 749 torr. So 749 torr, we need to convert that. 1 atmosphere is exactly 760 torr with that. And the volume they gave us in liters, so that looks out 421 liters. So it's easy to make mistakes with this equation. The way you check this equation is just make sure the units work out. So Kelvin cancels Kelvin, atmospheres cancel, liters cancel, torr cancels, and that leaves us with grams per mole. Grams per mole is what we want. And so this is the correct equation. So we'll do 1.67. Actually, let me do the 1.67 times 0.08206 times temperature would be 398 divided by 749 times 760 divided by 0.421. 131.45. So this gas has a mole mass of 131.45. And roll out 3 sig figs. So we'll just do 131.4 grams per mole. So again, let's take a look. They use the other R, 62.4. We got 132. So we got 131. We're pretty close. And so it's probably due around. Again, I use 4 sig figs for my R. They use 3 sig figs. And they use the other R, 62.4, which I don't recommend. So that's the molar mass of the gas. And so one thing is you can derive this equation or you can memorize it. Or you can do guess and check for the equation. Just make sure the units work out. The third application is density of a gas. The density, which our book uses capital D for, it's just the mass to volume ratio of the gas. It doesn't have to be a gas, this can be a liquid. But if it's a gas, then the gas obeys the ideal gas law in most conditions. And so what we can say here is this. The volume, we'll take the denominator again, the volume is equal to nRT over P. And then we're going to substitute this in here. And so we're going to get the mass divided by nRT over P, and then invert and multiply. So this is going to be the mass times pressure divided by nRT. One of the useful things with this is this, the mass over N. What does that equal? Mass over grams per mole. Grams per mole is just the molar mass. And so this is equal to the molar mass times P divided by RT. So this is the density equation here. The density, which is equal to the mass over volume, is equal to the molar mass times P over RT. So that's what we have here. Molar mass times P over RT. This is really useful because we don't have to do any experiments. So for example, if I want the density of helium, gas, I don't have to measure anything. I can predict what the density is as long as I know the molar mass and the desired pressure and temperature. So the molar mass of helium is off the periodic table. The molar mass of helium is 4.002 grams per mole. And so let's choose a temperature and pressure. So if I want the density of helium at any temperature or pressure, I just choose whatever temperature and pressure I want. Okay, what we're going to do is we're going to do the density of helium at 25 degrees C in 1 atmosphere. 25 degrees C is what we call room temperature, and atmosphere is 1 atmosphere is normal atmospheric pressure. This is normal temperature and pressure here. And so we'll just use the equation. The density of helium is going to equal the molar mass times the pressure of the helium divided by R times the temperature of the helium. So the molar mass is 4.002 grams per mole. The pressure of the helium is just 1 atmosphere. Let's just say exactly 1 atmosphere. Divided by R. R is 0.08206 liters times atmosphere per mole Kelvin times the temperature. The temperature is just going to be 298 Kelvin. One way to check if I got the right equation is just make sure the units cancel. So atmospheres cancel, moles cancel, Kelvin cancels, and that leaves me grams per liter. The gases densities are expressed in grams per liter rather than grams per milliliter because they're 1,000 times less dense. So we don't have to deal with small numbers. And so calculate the density of helium at these conditions. This is going to be 4.002 divided by 0.08206 divided by 298. 0.1636. Zero 0.1636. A lot of 36 base, so 0.164 grams per liter. What's the density of air approximately? What's the density of water approximately? Water is 1 gram per milliliter. What's the density of air approximately? 1 gram per liter. And so this is like, 10 times less dense than air. Less than 10 times. Would have been less dense. How would we do the density of air? Because air is a mixture. So let's do an additional calculation here. This would be an advanced calculation. The problem is what is the molar mass of air? Well, we know the composition of air. What is the composition of air? It's 21% oxygen. So this is how we figure out the molar mass of air. Air consists of 21 out of 100. So the mole fraction is 21 out of 100, or the percentage would be 21%. So 21 out of 100 molecules are going to weigh, well, what's the molar mass of oxygen? O2. Oxygen is 16.00. O2 will be 32.00. And so the molar mass of oxygen, pure oxygen, is 32.00 grams per mole. And so 21 out of 100 will weigh 32 grams per mole. And then the other fraction is 79 out of 100. 79 out of 100 will be nitrogen. Nitrogen doesn't weigh that much. Nitrogen weighs, well, nitrogen is 1401, and you have 2 of them, and so it's going to be 28.02. Although, air is a mixture, and mixtures don't have fixed composition, so I'm going to just say it is approximately equal to, not equal to, because we can have variations in this, of course. And so what is the approximate molar mass of air. Well, this is it's going to behave like, so I'll do 21 out of 100, or 0.21, going just from 0.21 times 32. And then this is going to be plus 0.79 times 28.2. And so the effective molar mass of air, if you averaged all the molecules, so if I said 100 molecules, what's the average of that? It's going to be 28.8. Okay, how many sig figs am I allowed? I'm not allowed that many sig figs. And so about 28.9 grams per mole. Actually, I'm not even allowed that. That's going to be about 29 grams per mole. I only have the composition to 2 sig figs, so this is 29 grams per mole. So if it were pure nitrogen, it'd be 28. If it's pure oxygen, it'd be 32. There's more nitrogen, and so the average is closer to 28 than 32. So it's 29 grams per mole. Well, okay, if that's the molar mass of air, then let's go ahead and calculate the density of air. The density of air is going to equal the molar mass of air times P divided by RT. Did I get this correct? I don't remember if I got this correct, but we can check it easily. And that is, the molar mass I got is 29 grams per mole, say, roughly. Maybe I shouldn't round here. Maybe I should round at the end, but it's all right. Times the pressure. The pressure, I'm going to use the same pressure, 1 atmosphere. R, 0.08206 liters times atmosphere per mole Kelvin. T, I'm going to have as 298 Kelvin. So this will be the same as the helium. Same conditions as helium. Actually, I have all the digits left in my calculator. I'll just use them. 1.18. You might get a little different answer because I rounded this one. I didn't round it since it was already in my calculator. Or about 1.2 grams per mole, grams per liter. So water is approximately 1 gram per milliliter. Air is about 1 gram per liter, 1.2 more precisely. Whereas helium is quite a bit less dense, at 0.163 or 0.2. Okay. This was density of a mixture that was in which we had to get the effective molar mass of the mixture. Okay, so what was that? Number 1, 2, 3. Now we're on 4. Is that correct? This might be different than the morning. So if you look at the morning molar mass and density. Actually, I already did that. Oh, this is molar mass and density here. sorry, this was already done in three. Three, I think, I combined a number of things. We're going to look at molar volume. So there was one other equation for the density there. If we weighed it, so for example, if we made the mass of air times the pressure divided by the moles in RT. Another way of doing it. Okay, the molar volume of the gas, MV, is equal to the volume per mole, V over N. And so 1 mole of gas occupies how many liters? Okay, we're going to do the same thing here. We look at N. N is equal to PV over RT. And so we'll substitute that in here. So this is going to be V over PV over RT. So V cancels, and then we flip that, so we're going to get RT over P. And molar volume is equal to RT over P. They ask you to memorize something here. 22.7 liters per mole. This is the molar volume at STP. STP stands for standard temperature and pressure here. And so, at STP, standard temperature, do you know what that is? Standard temp and pressure. Standard temperature is 0 degrees C. Standard pressure is 1 bar. And so this is the molar volume of a gas at 0 degrees C and 1 bar pressure. Let's go ahead and calculate it. The molar volume is equal to R. I don't even remember what value R. Liters atmosphere per mole solid. Times the temperature. The temperature of 0 degrees C is 273 Kelvin. Divided by the pressure. The pressure is 1 bar. We need to convert that into atmospheres. Do you know the conversion? 1 atmosphere is equivalent to 1.01325 bar. So let's make sure the units work out. Kelvin cancels, atmospheres cancel, bar cancels, and we're left with liters per mole. What we end up here with is 22.7 liters per mole. When I was taking Chem 4, I had to memorize it. Although my number was different. This is the new version. The old one was like that, 22.4 liters per mole. The difference between the new version and the old version is pressure. This was at 1 atmosphere, not 1 bar. The new one's for 1 bar. Since the bar is a little bit lower pressure, the volume is a little bit bigger. The lower the pressure, the bigger the volume. The higher the pressure, the smaller the volume. And so this has a little higher pressure, and therefore the volume is a little smaller. I had to memorize this, so I did. I memorized that. They're asking you to memorize this one, the new one. You don't have to memorize the old one. $22.7. So I memorized this one. Do you know how many times I've used it since? Like 0. 0. That was a waste. I spent time memorizing that. You know why I used it so little?
Because did it not feel the calculation already? Like on the timer? It's like sometimes they give the
Yeah, sometimes. Well, I'm talking about on maybe on exams I might have used it once or twice. Like the midterm I probably used it. What is STP? STP, standard temperature and pressure. What is standard temperature? 0 degrees C. What is standard pressure? 1 atmosphere. Now it's 1 bar. But in chemistry lab, I never used it. Do you know why? I never used it because of this. At 1 atmosphere and 0 degrees C. Our lab was, the thermostat was not set at 0 degrees C inside our laboratory. In fact, you know, if it were set at 0 degrees C, all the ice would freeze. I mean, not the ice would freeze, the ice is already frozen, all the water would freeze. I would have probably picked a different major. You know, can you imagine if all the labs were at 0 degrees C, how uncomfortable it would be? It would work. So that's the reason why I memorized this, but I never used it. I never used it because I never worked in a lab at 0 degrees C. Some gas catalogs have things referenced to STP. That's okay. Then you might use it, but you don't really use it much in practice. And so let's do this. What we're going to do is we're going to calculate the molar volume at RT. What's RT? RT stands for room temperature, and room temperature is more reasonable. RTP. Except this P we're going to do with 1 atmosphere, not 1 bar. RT is room temperature, and that's 25 degrees C or 298 Kelvin. So let's calculate the molar volume at RTP. Molar volume is going to equal R 0.08206 liters times atmosphere per mole Kelvin. RT over P. T is going to be 298 Kelvin over P, 1 atmosphere exactly. And so what does that come out to here? .08206 times 298 divided by 1. A little bit of delay. 0.08206 times 298. .4445 meters per mole. So we're allowed 3 sig figs. So this is going to go to 24.5 meters per mole. And so 1 mole of gas at room temperature and atmospheric pressure is 24.5. If I cool that gas to 0 degrees C, the volume contracts to 22.4. If I change the pressure a little bit, you know, to bar instead of atmospheres, then the gas expands to 22.7. If you're going to memorize one of these, I would probably memorize this one. This one would be more useful. But you don't have to memorize any of them because it's an easy calculation. But it's nice to have this one memorized. When we do stoichiometry, I'll show you. what I mean by that. Yeah. We can calculate the molar volume at any temperature and pressure. We'll just plug that in. So this one's at a cold temperature. At cold temperature, the volume contracts or shrinks, but it's at a low pressure. A low pressure volume expands. And so the molar volume under these conditions is 40.6 liters per mole. And so it looks like the low pressure really caused it to expand, not so much the temperature after here. It doesn't matter what the gas is. This applies to all the gases. So we're going to go to gas stoichiometry next. Gas stoichiometry, there are a lot of ways that deals with gas stoichiometry. Let's take a look at the ways. The standard stoichiometry map is we have grams of A, and then we go to moles of A. And then from moles of A, we go to moles of B. And from moles of B, we go to grams of B. A problem is weighing gases. Weighing gases is not so easy. So if A is a gas, I'd rather not weigh it. Instead, I'd probably measure its volume. So we'll have volume of A up here. And A has to be a gas in this case. So if I want to go to moles, I can, straight from here. Because I have a ratio that relates moles and volume. It's called the molar volume. And so at STP in bar, it's 22 point, what was it, 22.7 or 22.6? Or 22.7 liters per mole. 22.7 liters per mole. So that, if I flip this over, that allows me to convert from liters to moles. 1 mole of gas occupies 22.7 liters of any gas. At RTP, I'll do this conversion using this one, 24.5 liters per mole. Room temperature and atmospheric pressure. This is very, this would be bar. This would be an atmosphere. And neither STP or RTP, I'm going to have to use the molar volume and calculate it. The molar volume is equal to RT over P. Or I could use the ideal gas law. Ideal gas equation. The moles N is equal to PV over RT. So I can just do an algebraic calculation. So these are the ways I can go from volume of A gas to moles of A gas. And the same thing here. If B is a gas, then I could do the same thing. That is, if B is at STP, then I just use 22.7 liters per mole. If you want to memorize it, you don't have to memorize it. If it's at RTP, room temperature and normal atmospheric pressure, this would be an atmosphere, then it's 24.5 liters per mole. If it's at neither of those, then we calculate the molar volume. The molar volume is equal to RT over P. Or if we don't want to do any of these, we just use the ideal gas law. Ideal gas law says that the volume is equal to nRT over P. And just plug those in. So take a look at this reaction here. This one. Not this one. Oh, there's one more. I forgot. One more is to use Avogadro's law. The mole ratio is the same as the volume ratio. If T and P are constant. That is, if A and B are under the same temperature and pressure, then this is the quickest. Mole ratio is the same as volume. Okay, so let's take a look at some stoichiometry problems here. Number 29. One small-scale laboratory method for preparing oxygen is to heat potassium chlorate in the presence of a catalyst. So this is a reaction we actually do in Chem 1A. We'll take 2 potassium chlorate, heat it up, it decomposes into potassium chloride solid and oxygen gas. This Avogadro's mole ratio is equal to volume ratio of T and P are constant, and both are gases. In this case, it doesn't work here in number 29. We're going to do number 29 modified. They want STP volume. Well, what we're going to do is we're going to change STP to RTP, is room temperature. And so the equation is this: 2KClO3, 2 potassium chlorate, solid, it's a white solid. You mix it with a little bit of MnO2, which is a black powder that acts as a catalyst to speed up this decomposition. It decomposes into KCl and O2 gas, 3O2 gas. So if I had 2 liters of KClO3, how many liters of oxygen would I produce? Well, you might say 3. The mole ratio is correct. It's a 2 to 3 mole ratio, but the volume ratio is incorrect. It's not a 2 to 3 volume ratio. And the reason is because KClO3 is a solid and O2 is a gas. If KClO3 were a gas and both these gases were at the same temperature and pressure, then it would be simple. I'd need 2 liters of KClO3 for every 3 liters of O2 that's produced. But since KClO3 is a solid, then we can't do that. And so we'll just have to use regular stoichiometry. Using regular stoichiometry, I have 5.74 grams of KClO3. And so what I'm going to do is I'm going to go from grams of KClO3 to moles of KClO3. From moles of KClO3 to moles of O2. And then from moles of O2, I'm going to go to volume of O2. But I have so many choices in going from volume. You know, I could use the STP, I could use the RTP, I could use just the molar volume just calculated if I forgot STP or RTP, or I could use the ideal gas law. Well, this is why you might want to remember RTP. And so let's go ahead and set up this stoichiometry here. 5.74 grams of KCl3. I don't want to look at calculate. I don't want to calculate the molar mass of KCl3. So I'll look it up. The molar mass is here, 122.55 grams per mole. And so 1 mole of KCl3 weighs 122.55 grams. Grams of KCl3 cancel, and that leaves us with moles of KCl3. So I go from grams of KCl3 to moles of KCl3, moles of KCl3 to moles of O2. And so we have 3 moles of O2 for every 2 moles of KCl3. So moles of KCl3 cancel, and that leaves us with moles of O2. Since this is RTP, I memorized it. If I memorized it, then it's 24.5 liters of gas per mole of gas at RTP. And so this might be a useful number to memorize because we usually work at room temperature and normal atmospheric pressure. And so what does this give us? So we got 5.74 divided by 122.55 times 3 divided by 2 times 24.5, 1.721 liters. Okay, they did it at STP. So if I go from room temperature to freezing, the gas is going to shrink, it's going to contract. And so if we did this at STP, the volume would be a little smaller. And so we can take a look at what volume they got. The answers here. They got 1.59 liters of O2. We got 1.72 liters of O2. The reason ours is bigger is because we're at a warmer temperature. Warmer temperature gases expand, colder temperatures gases contract. That's what we end up with. A significant difference. It's 29. Let's look at number 31. We're going to do number 31 at RTP instead of STP. If we did this at STP, we might have to worry about water freezing. Or something freezing. And so the first reaction was we could generate oxygen gas. This reaction generates oxygen gas. And we could do this small scale, take potassium chlorate, heat it up. This next reaction generates chlorine gas. And so all we do is take potassium permanganate and HCl. It looks like a double replacement, but it's not. This is redox, and we can figure out using the chart method that permanganate's a powerful oxidizer. So if we take 2 KMnO4s plus 16 HCl, it's going to yield 2 MnCO2s plus 5 chlorine gas plus 8 H2O. H2O is usually listed as a liquid, not aqueous. Because water dissolved in water sounds funny. So H2O liquid plus 2 KCl to be aqueous. Chlorine's non-polar, so it bubbles out. Solution. HCl is very polar. That gas stays in solution. HCl is a gas, chlorine's a gas. HCl loves water, chlorine wants it. So that's why HCl is aqueous instead of a gas. So we have 9.81 liters of chlorine. So 9.81 liters of chlorine. And then we can't do a volume to volume here because KMnO4 is an aqueous solution. It's not a gas. So we have to go from liters of chlorine to moles of chlorine. Well, if we're at RTP, then it's easy. Because at RTP, it's 24.5 liters per mole. And then we're going to go from moles of chlorine to moles of KMnO4. And then from moles of KMnO4, we're going to go to grams of KMnO4 using the molar mass. So let's set this one up. It's going to be 9.81 liters of chlorine. And then at RTP, 1 mole of any gas occupies 24.5 liters. And so in this case, the gas is chlorine. And 1 mole of chlorine gas occupies 24.5 liters. And that's going to give us moles of chlorine. And then from moles of chlorine, we'll go to moles of potassium permanganate. So it's 2 moles of potassium permanganate, KMnO4, for every 5 moles of chlorine. And then we'll just look up the molar mass of potassium permanganate online. 158.03. 158.03 grams of KMnO4 per mole. Okay, so the liters of chlorine cancel out. Moles chlorine cancel out. Moles of KMnO4 cancel out. That leaves us with grams of KMnO4. So we just calculate this. Again, this was at RTP. And so this is good at RTP. If we did this at STP, then you'd really want to memorize that number for a lot of calculations at STP. And there are a number of calculations at STP here. What if we aren't at RTP or STP? Then what do we do? And so let's look at number 33 here. Number 33 is not at standard temperature. Temperature is 214, and it's not at room temperature. And this is not at standard pressure in bar, which is 1 bar, or standard pressure in atmosphere, which is 1 atmosphere. They're different. So we have a choice here. So we got FeS2. FeS2 is a strange one. This is called iron disulfide, or pyrite. And pyrite has a weird anion. This is an anion you didn't have to memorize, but it's iron 2 cation, and it's going to be the S2 minus anion. This is called disulfide, this anion. So this is iron disulfide. Gold. So if we take some pyrite, maybe 4 of these, and roast it in air, which is going to have 11O2 gases, it's going to give us 2 Fe2O3 solid, which is brass, plus 8 SO2 gas. How many liters of SO2 gas measured at 983 torr or 214 degrees C are produced by the reaction of 598 grams of FeS2? So we're going to go 598 grams of FeS2 iron disulfide, to moles of FeS2. From moles of FeS2, we're going to go to moles of SO2. And then from moles of SO2, we're going to go to volume of SO2, because SO2 is a gas. Okay, this is not a standard temperature. This is not at room temperature. And so either we calculate the molar volume here, or we use the ideal gas equation. So if we calculate the molar volume, then we need the molar volume under these conditions. The molar volume under these conditions is, well, molar volume is equal to RT over P. So 0.08206 liters times atmosphere per mole. RT, T is 273, 487 Kelvin. We add 273 to that. RT over P. P is 983 torr. And then I need to convert that to atmosphere. 1 atmosphere is equivalent to 760 torr exactly. So I need a new molar volume here. And so the new molar volume is going to be 0.08206 times 487 divided by 983 times 760. Molar volume is quite a bit bigger. It's 30.897 liters per mole. It's quite a bit bigger because this temperature is high. And although it should be smaller because the pressure is higher, but the pressure is not that much higher. And so we either use this as a conversion factor, or we use the ideal gas law. The ideal gas law is V is equal to NRT. So we just do a second calculation for that. So either one, we can do both for this one, but we're out of time, unfortunately. So I'll do both next time.